Hello, my chemist extraordinaire. Welcome. It's so nice to have you here with me. We are going to continue with some acid-base chemistry, and this is actually a continuation of the previous video where I talked about Kw, the autoionization equilibrium constant for water, and Ka, and began just barely introducing Kb. Okay, so let us begin with looking at my calculator. So in the previous video, I mentioned how my calculator always has the funniest, weirdest looking stuff. Whenever I open it up, I look at it and I don't know what it is. It's like alien messages or something, and it's always different. So look at this today. Oh my gosh, it's so funny and weird and cool. I love it. Okay, but now that we've done that, we can start with looking at Ks and Kbs. Okay, the acid ionization constant and the base ionization constant. Okay, so I'll start out with getting my lovely fountain pens, as I do. I love these things. Oh my gosh. When I started this channel, I used calligraphy pens where you dip them in the ink, and there was just too many errors, meaning like big blobs of ink, and it was just kind of a mess, so I transitioned to fountain pens. Okay, so let us dive right in, and once again, as with the last video, we'll look at weak acid equilibria, but we'll also look at base equilibria. Okay, so we will be looking at definitely working with Kas and Kbs. Kw will be incorporated as well. Okay. Alright, so the first place I want to begin is talking about and just reminding you, reviewing you, with you, Bronsted-Lowry equilibria, Bronsted-Lowry acid-base theory. Okay. And essentially that's recognizing that an acid-base reaction is a proton exchange reaction where a hydrogen ion goes from one species to the other. Okay, so let's consider the conjugate acid-base pair. And I'll remind you this concept, conjugate acid-base. Okay, we're going to look at NH4 plus and NH3. Okay, so let's look at these and see how are they related to each other. Okay, here we have NH4 plus and NH3. So this species here has an additional hydrogen and a positive charge. So essentially, if you took NH3, which is ammonia, and you added hydrogen ion H plus to it, you would get ammonium here. Okay, so this is the conjugate acid this is the conjugate base. I do have at least one video where I review Bronsted-Lowry acids and bases, and I go through this whole concept. So if you wanted to watch that video first, you could do that. Okay. But what we are going to consider is, what if you have NH4 in solution, and how would it act as an acid? We say here it's an acid. What does that mean? That means it is a hydrogen ion donor. Okay, conjugate base. Bronsted-Lowry theory says that this is an H plus acceptor. Okay, so we can look at each one of these and look at the kind of equilibria that would exist for them in aqueous solution. So in the case of our ammonium ion NH4+, it would look like this. We'd have our NH4+. This is aqueous. Okay. And because this is a donor, essentially means it's losing. It can lose a hydrogen ion. When this loses a hydrogen ion, it becomes NH3. It's also aqueous and H plus. Okay. So here is the acid dissociation equilibrium that occurs for ammonium. Okay. Now what about the conjugate base NH3? Okay. What that can do is it can react with water and because we're looking at it as a base here, that means it's a hydrogen ion acceptor. So it is accepting an H plus ion from the water. Okay, so we have then ammonia is formed when that happens. And since one of the hydrogen ions came from the water molecule, that leaves behind a hydroxide ion. Okay. So here we have the acid dissociation constant, or I should say acid dissociation equilibrium for the conjugate acid, ammonium. And we're also showing the base equilibrium that occurs with ammonia. Alright. And we can also recognize what are the equilibrium constant expressions for each of these. So we could write those out here. Okay. So this is we're looking at an acid, and we're looking at an equilibrium constant. And so we would write products over reactants. Anything that where you could measure the concentration. So we have NH3 times H plus over reactants, which is NH4 plus. Okay, so that's the equilibrium constant expression for Ka. Meanwhile, here we're looking at ammonia behaving as a base. And so we call this equilibrium constant Kb, because we're looking at NH3 as a hydrogen ion acceptor in this equilibrium. Okay, so once again we have products over reactants. So we write this out as NH4 plus times hydroxide and divide it by the reactants. Okay. So remember, in equilibrium constant expressions, you cannot include a pure liquid or a pure solid. So water will not appear, but ammonia can appear. Okay. All right. So look at these two equilibria and how they are related to each other. And what I wanted to do is consider, what if both of these are happening in solution? And when that's the case, you can actually add up these chemical equations. Okay? And you can do that when you have simultaneous chemical equations or equilibria occurring in solution together. And in this case, you can add them up, and because NH3 appears as a reactant and as a product, those can actually cancel out, and same with our NH4. So let's look at what this looks like. Why don't we just write these all out? All of the reactants we can include here. So we have our NH4 plus, and I'm going to be lazy. I'm going to now exclude the phases, okay? We're going to just make room here for everything that we have. H3 plus H2O. Okay, and now we can add up all the products on this side. We have NH3 and H plus and NH4 plus and hydroxide, OH minus. Okay, so now look what we can do. We can make a matter pen here. We can recognize that ammonium, NH4 plus, is on both sides. So we can cancel that out. What else appears on both sides? Are ammonia and NH3. Okay, what does that leave behind? Well, we have water. And H plus and OH minus. What is this? This is the auto-ionization of water. Okay, and we've seen that before in the previous video, and even if you didn't watch the previous video, we could write out the equilibrium constant expression for this, remembering that this is liquid water and these two are aqueous. We would have products over reactants, in this case just one because it's a pure liquid. So this looks like this. Alright. Now, this is actually consistent with what we have just recognized here with an equilibrium and an equilibrium constant expression. Adding it together with another equilibrium and its equilibrium constant expression constant expressions to give the resulting equilibrium constant expression for the resulting equilibrium. And let's just test and make sure that this is true, that this is consistent. Okay, so here's our question. If we multiply Ka times Kb, does it equal Kw? Let's try it out. Let's take this Ka expression here, NH3, H plus, divided by ammonium, NH4. Okay, so there's our Ka. Let's multiply it by the Kb, which is NH4 plus. There's our hydroxide. And here's our NH3. Okay, what does this equal? Well, let's look. We have, I'll get my red pen again. That was kind of fun to cross those out. Okay. We have NH3 in the numerator and in the denominator, so those will get canceled out. And we have NH4 in the denominator here, which cancels out with the numerator here. And lo and behold, what does that leave? H plus times OH minus, which indeed is the same as Kw. So this allows us to do all sorts of calculations and determinations of, and I should say, no longer is that a question. It is a yes, right? We just showed this to be true. Check. So, if we know the Ka value for an acid, but we do not know the Kb value for its conjugate base, we could calculate it because we know what Kw is. Kw is a constant. That is a known value that has been measured many, many, many times over. Times 10 to the minus 14. Okay, so knowing this constant for water, then it allows us to determine either a Kb that's unknown or a Ka that's unknown. So this can be very useful in acid-base chemistry in that way. So let's do an example of a calculation and see how this works, okay? So I have run out of room on my paper here. So I'll put my pens away for a second. And let's flip our paper over. Okay, let's do an example. Alright. Would you like to switch colors? I have some blue ink. Switch it up a little bit. Okay. Alright, let's look at this problem here. Let's calculate. This will be an example of calculating a Kb value for a base where we don't know the Kb value, but we do know for its conjugate acid. Okay, so let's calculate the Kb for, let's look at the carbonate ion. Okay, so here's what we want to do. Okay, but I'm going to give you what is known. Now, this is something where you could look on a table of Ka values, okay, to determine this. The Ka of bicarbonate. Okay, so bicarbonate, HCO3 minus. You could look this up in a table. And in the table that I used, I saw that its value was 5.6 times 10 to the minus 11. One thing I wanted to let you know is that sometimes you look in different textbooks or different sources with tables of Ka values, and they can vary slightly. So just wanted to give you the heads up. Okay. So let's look at this. Okay. So CO3 2 minus. Just to remind you, this is the conjugate base of HCO3 minus bicarbonate. And we can see that if we remind ourselves of what carbonate can do in solution. Okay, so carbonate can react with water. And there's this equilibrium that goes on where this is acting as a base. So if you remember what that means in Bronsted-Lowry theory, it is a proton acceptor. So it is gaining a hydrogen ion from the water to become bicarbonate. And once that hydrogen ion leaves water, that leaves hydroxide. Okay. Sorry. This is the base equilibrium. In other words, the Kb. Now, we don't know what the value is yet, but we do know that the Kb expression would be products over reactants. Okay. And what else do we know? We know that Ka times Kb for a conjugate acid-base pair equals Kw. Alright, what we don't know yet is Kb, so we can solve for Kb here. Which is Kw divided by Ka. And remember, this would be the Ka for HCO3 minus the conjugate acid of the carbonate ion. Alright, so it looks like we are set to do our calculation and get the final answer. possessed by aliens. Okay. 1.00 times 10 to the minus 14. And just as a reminder, equilibrium constants, those values are unitless. Okay. And then divide it by Ka. That is known. That was part of the initial problem. It was given. We looked it up on a table. The Ka of bicarbonate is 5.6 times 10 to the minus 11th. 5.6 times 10 to the minus 11. Okay. Alright, what do we get? Let's see. It still cracks me up. You know, I really need to watch this, like, as the hours go by and see if it, like, slowly changes or if it just suddenly changes. I have no idea. It's so funny. Okay. But there it goes. Alright, we have 1 to the minus 14th divided by 5.6 times 10 to the minus, oops, oh gosh, sorry. I guess I didn't hit that button hard enough. Minus 14, okay. Divided by 5.6 to the minus 11th equals, okay. Now, how many significant figures do we get? We only get 2 here. Alright, so 1.8 times 10 to the minus 4. Okay, so there is our Kb for carbonate. Also wanted to point out that you can see how the acid-base strength is related with these conjugate acid-base pairs because their product equals a constant Kw. As the Ka value for the conjugate acid gets larger, that means that the Kb value for the conjugate base gets smaller, and vice versa. So the stronger the conjugate acid is, the weaker the conjugate base is, and vice versa. Alright, so that's how mathematically that relation can be seen. Okay. Alright, so I hope this has been helpful for you. And as always, please let me know if you have requests, if you have questions, if there's anything you're wondering about or any topics you would like me to cover. Okay, I would love to do that for you. If you do find this channel to be helpful for you, please consider subscribing. It does help this channel to grow and helps more people find it, and hopefully I can help more people that way. I really do hope that this is a way of learning that helps people who maybe don't like the really high energy, frantic, kind of get your attention kind of modality. That's obviously what this channel is not about. This channel is about learning chemistry in a very slow, methodical, soothing way. That's my intention. And I hope you find it to be helpful, whether it's to learn chemistry or if it is just to relax. Either way, that makes me very happy. So thank you for being here with me,